Today in Lecture 5, we will cover Section 3.2. At the end of today's lecture, you should be able to draw a circuit network and understand the principle of equivalence. You should also be able to understand and apply Kirchhoff's current law, abbreviated by KCL, and understand and apply Kirchhoff's voltage law, abbreviated by KVL. To begin, we will talk about circuits. There's a variety of ways to draw circuits. In the picture below, we have element 1 with current I1 flowing through it connected to element 3, as well as elements 4, 5, and 6, each of which has currents I3, I4, I5, and I6 running through them. We see element 3 is connected to element 2, which is also connected to elements 4, 5, and 6. Element 2 has current I2 running through it. Now this depiction is rather messy. What we want to introduce is a formal way to draw circuit elements. The correct way to draw a circuit element is as follows. In the picture below, we have elements 2, 3, and 1 connected in series. That is, they are connected in line, and the current flowing through them has no branch. That is, current I1 runs through element 1, I3 runs through element 3, and I2 runs through element 2. Now elements 4, 5, and 6 are drawn as follows. They are connected in a parallel configuration. For elements 4, 5, and 6 all share the same node at top and bottom. Now, these elements are connected with traces. Traces are lines represented as follows that are assumed to have zero resistance. Our elements are oriented vertically or horizontally with traces drawn in a horizontal or vertical fashion. Sometimes traces will be drawn diagonally. Now a node is where two or more elements are connected, and we label these as A, B, C, D, and as follows in the alphabet. Now we see element 1 and 3 are connected via node A. Elements 2 and 3 are connected via node B, and elements 1, 4, 5, and 6 are all connected by node C. Node C encompasses the connections of elements 1, 4, 5, and 6. We note that C can encompass more than one junction of our traces. Last but not least, node D connects elements 2, 4, 5, and 6. Now, we will introduce the principle of equivalence. For two electrical circuits to be equivalent, the following has to be satisfied. We have to have the same number of nodes within our circuits. We have to have the same number of elements within our circuits, and the same nodes have to connect the same elements within our circuits. Now consider the following example. We have our circuit from previous, shown in the top left, where we have elements 2, 3, and 1 connected in a series fashion. Element 1 is connected to elements 4, 5, and 6 by node C. Element 2 is connected to elements 4, 5, and 6 via node D, where 4, 5, and 6 are existing within a parallel fashion. Now, which of the following circuits are equivalent? Let's start with our circuit to the immediate right of our original. We have elements 1, 3, and 2 connected in a series fashion, which are connected in a parallel configuration to elements 4, 5, and 6. We can say these two are equivalent, even though the circuit on our right is drawn in a vertical fashion. Now let's proceed to the circuit to our immediate right. We have elements 1 and 4 connected in a parallel fashion. We do not have this in the original circuit, so immediately these two circuits are not equivalent. Now let's look at the circuit on the right top. We have elements 1, 3, and 5 connected within a series fashion, which does not represent our original circuit. Thus, these circuits are not equivalent. Moving to the bottom left, we have elements 1, 3, and 2 connected in a series fashion that are connected to elements 4, 5, and 6 within a parallel fashion. Elements 4, 5, and 6 can be connected to node C, and node D at top and bottom. What's unique is, since elements 4, 5, and 6 share the same nodes, we can switch their order, such that the element on the bottom left is equivalent to the circuit on our top left. Now progressing to the middle circuit on the bottom, we have elements 3 and 4 in a parallel configuration, which immediately indicates these two circuits are not equivalent. And last but not least, bottom right, we have elements 1, 3, and 2 connected in a series configuration that are now connected to elements 4, 5, and 6, which exist in a parallel configuration connected by nodes C and D. The circuit is equivalent to our original.